The temperature of the freezer compartment in our refrigerators usually ranges between -18 and -20 degrees. If we could lower this temperature to a point close to -273.15 degrees, we would be very close to absolute zero, and the atoms would become almost motionless. So what would happen then, do you know? In the universe, we would get very close to detecting the most mysterious substance, dark matter. Because the vibrations of the atoms would decrease to a minimum, the vibrations created by dark matter would become detectable. Of course, for this we need something different from a refrigerator: quantum detectors.
Dark matter is the most abundant type of matter in the universe. It makes up about 85% of the total matter in the observable universe. What is the matter we know made of? It's made up of components like protons, neutrons, and electrons, right? In dark matter, none of these exist. So how is it that we can't see the most abundant type of matter in the universe at all? There's actually a very simple reason for this, folks. For a substance to be observable, it needs to interact with light. But dark matter doesn't interact with light at all. But how can we be so sure about the existence of something we can't observe? In the end, dark matter is a widely accepted view in the scientific community today. The reason we can be so sure is that it has gravitational effects. For example, stars in the outer regions of galaxies need gravitational influence to rotate. But this rotation speed can't be explained just by the visible matter. To explain this speed, we need more mass. This is where the mass of dark matter comes into play. Another example is that it bends the light from distant galaxies behind large structures like galaxy clusters, changing their appearance. This is called gravitational lensing. For this effect to occur, more mass than the visible matter is needed. This extra mass requirement is met by dark matter. Here's another piece of evidence. The cosmic microwave background radiation is evidence left over from the Big Bang, right? The size and distribution of the fluctuations in this radiation tell us that there is a certain amount of dark matter in the universe. The formation of the universe's large-scale structures like voids and superclusters can't be explained without dark matter. It is thought that dark matter enables the formation of these structures, by gravitationally bringing matter together. So you can think of dark matter as a kind of glue that holds the universe together. Now, when we cannot observe a substance for which there is so much evidence, the mystery of this substance naturally increases even more. Scientists have been working for many years to solve this mystery. They're developing methods to detect dark matter. Measurements occur in a lab under Gran Sasso Mountain, Italy. For example, sensitive measurements are being made in a shielded environment, protected from cosmic rays using underground detectors placed deep in the Earth's crust. For example, this laboratory is located under Gran Sasso Mountain in Italy. That's actually where the name comes from. The Gran Sasso Laboratory is surrounded by about 1,400 meters of rock. So this place is largely isolated from cosmic radiation. So, it's a very ideal environment for particle physics experiments. This detector here, called Xenon 1T, is trying to detect dark matter signals. The detector has obtained some important data during its operation, but we still don't know if these signals belong to dark matter. This detector, called LUX-ZEPLIN, located in South Dakota, USA, is considered the most sensitive dark matter detector in the world. In 2022, it conducted its first test 1.5 kilometers underground. In trials lasting over 3 months, it also obtained significant data, just like Xenon 1T. But it hasn't reached a conclusion yet. There are also some tools that try to indirectly detect dark matter. Cosmic ray detectors are one of them. Dark matter particles can interact with normal matter in the atmosphere, although very rarely. As a result of these interactions, cosmic ray detectors pick up high-energy particles, or gamma rays. But of course, these rays aren't always specific to dark matter. Also, atmospheric events or other cosmic occurrences mislead these detectors. Satellite-based telescopes can also indirectly prove the existence of dark matter. Dark matter bends the fabric of space-time due to its mass, causing light from behind it to bend as well. These telescopes can observe this phenomenon and detect the presence and distribution of dark matter. However, such observations require vast amounts of data, and analyzing the results can be time-consuming. As you can see, each method has its drawbacks. Now I'm going to talk to you about the most innovative and perhaps most promising method outside of these. I also gave a hint at the beginning of the video. Quantum detectors are getting closer to unraveling the mystery of dark matter. These detectors operate at extremely low temperatures, leveraging the principles of quantum mechanics to make highly precise measurements.
When I say extremely low temperatures, I don't mean something like -80 or -90 degrees. I'm talking about a point very close to absolute zero.
The value of absolute zero is -273.15 degrees Celsius.
This is a point very close to that temperature. Let me give you an example to help us understand this cold. At the Vostok station, in Antarctica, the coldest place on Earth, temperatures can drop to -89 degrees. But even this is much higher than the temperatures at which dark matter detectors operate. Temperatures close to absolute zero are 184 degrees below this level.
In such a cold environment, the vibrations of atoms can decrease so much that they become almost motionless. This way, even the very weak interactions caused by dark matter particles can be detected. The detectors, called Super CDMS, were designed specifically for this kind of task. Located 2 kilometers underground in a lab in Ontario, Canada, these detectors were completed last year. These have more advanced technology than previous 1N models and focus on detecting dark matter particles in the low energy range. By using silicon and germanium crystals, they can hand measure the interactions of particles with matter with high precision. These detectors use a technique called cryogenic N cooling to operate. Coolants, like liquid helium and liquid nitrogen, bring the temperature down to values close to absolute zero. Scientists hope to obtain clear results in such an environment thanks to low radioactive noise.
But why is detecting dark matter so important? What will happen once we detect it? What will this dark matter be useful for? These questions inevitably come to mind.
First of all, understanding this mysterious type of matter is crucial for us to grasp how the universe was formed. For example, galaxies. Dark matter plays an important role in their formation and evolution. Galaxies are shaped in the gravitational wells created by dark matter. If we understand the force that holds all of this together, that is, dark matter, we will also have understood the structure and dynamics of galaxies.
Is it just galaxies? No. We can also uncover the secret of the cosmic web that holds those galaxies together.
If you follow this channel, you might remember. I prepared a video explaining the similarity between the cosmic web and the human brain. Perhaps the mystery of how these cosmic webs form will become much clearer once we can detect dark matter. Evidence for dark matter comes from the cosmic microwave background radiation. Fluctuations show its gravitational impact. Understanding dark matter reveals the structure of the universe. The fluctuations in this radiation reflect the gravitational effects of dark matter during the early times of the universe. If we can understand dark matter, we can also grasp the distribution and structure of the universe in its first few 100,000 years. Dark matter is also important for understanding the rate of expansion of the universe.
As you know, dark energy is accelerating the development of the universe.
While dark energy is increasing the rate of expansion of the universe, dark matter creates strong gravitational effects that prevent the universe from expanding too quickly. There is a balance between these two, dark matter and dark energy. Detecting dark matter will help us understand this balance better. Alongside all this, we could also gain insights into the future of the universe. Because if the gravitational effects of dark matter become dominant over dark energy, the expansion of the universe could stop or even reverse. If such a situation occurs, the universe would collapse in on itself, leading to a scenario known as the Big Crunch.
Of course, all of this is about the relationship of dark matter with space. So, how can the detection of dark matter benefit us outside of cosmology?
As we understand the nature of dark matter, we may discover new energy sources. These studies could lead to entirely new methods of obtaining energy, potentially cleaner and more sustainable than fossil fuels. Additionally, research on dark matter could offer new insights into nuclear fusion.
So, it's not just dark matter itself, but the methods we use to study it can also provide many benefits.
For example, the advanced sensor technologies used in the discovery of dark matter could improve the precision of medical imaging devices. This could lead to the development of more effective treatment methods in fields like radiotherapy. Similarly, superconductors and other advanced materials used in dark matter research could help create more efficient energy systems by reducing losses in energy transmission. With these advanced materials and sensors, renewable energy sources can also be utilized more effectively.
Of course, there's also the other side of the coin.
Throughout history, scientific and technological advancements have brought both great benefits and significant risks. Unfortunately, such discoveries often come with potential dangers and opportunities for misuse. Isn't atomic energy the clearest example of this? On one hand, it provides clean energy through nuclear power production. On the other hand, it has led to the development of nuclear weapons.
Theoretically, the use of dark matter could also trigger reactions at very high energies.
These reactions could result in explosions or radiation releases, causing serious harm to the environment. Just as the uncontrolled use of nuclear energy led to disasters like Chernobyl, a similar scenario could potentially occur in the future due to dark matter.
So everything depends on humans, just as important as these discoveries is how they will be used. With the discovery of dark matter, humans will, once again, discover their own dark side along with the bright side of science. As for which one will win, only time will tell.